So, I have already told you that we are basically going to discuss about the single component phase diagrams here, and in a single component phase diagrams the composition variables is fixed, like you consider pure water, pure iron, pure carbon dioxide, there is no change of compositions. So, the variables which do get changed are temperature and pressures. So, we must now look at what is the effect of pressure on these systems. Until now I have told you, I have shown you that the free energies of different systems or different phases as a function of temperature keeping pressure constant. Now we are going to see if I change the pressure what will actually happen and how we can get the phase diagrams. Please be attentive while looking at these diagrams. Let us suppose I have free energy versus temperature curve at the top at a fixed pressure 1 atmospheric pressure, and I know that these two curves will cut or cross over at a melting temperature given by this point here, okay, which has been marked by a red dot. So, now can I just translate this point onto the pressure temperature diagram? How I do it? Very simple, I just draw a vertical line across that. So, I could see that this temperature Tm vertical line cuts the pressure line at a point, and this point is given by a blue dot. So, now if I change the pressure, this is 1 atmospheric pressure, if I change the pressure what will happen? Suppose I have a pressure at P, P may be higher than the atmospheric pressure, that is what is shown here. So, if I have higher than the atmospheric pressure, the free energy curves will be changed little bit. The change means the nature of the curves will not change, but the point at which they will intersect will change. That is what is shown here, it is getting intersected at a different point than the PBS point, and this is given by the new point. Now, if I can translate the temperature at which they cut to the pressure temperature axis, I get a new point, new blue point. So, this is the way actually I can generate many such blue points. You can see here one by one I can generate many such blue points as a pressure temperature equilibrium, and also at a pressure less than the atmospheric pressure I can have a point, and this is the way I can get a boundary. What is this boundary? This boundary is between solid and liquid, like suppose water and ice, liquid water and ice, this boundary. So, I can have a boundary between solid and liquid. So, immediately you can see this is a phase diagram between solid water like ice and liquid with a boundary line as where the axes are temperature and pressure. So, we all know that this curve or this line will have a negative slope. Why? That is very simple. If you know that the melting temperature of ice will get reduced if I apply pressure, because ice has a lower density than water, therefore ice expands when it forms from water, and therefore if I apply pressure it will try to reduce the volume and then it melts at lower temperature. So, that means the slope of this curve dP by dt will be negative. That is why this curve is shown as a negative, but if it is not so for many other metals, that this change of temperature versus pressure is not negative, in that case it will have a positive slope. So, now let us do it for that temperature at which this 1 atmospheric pressure line cuts this axis is given as a 273 K, that means 0 degree Celsius. So, let us now do some calculations. I will do it on the board, that is easy for you to follow. Let us know that along this line we know the solid and liquid are equal along this line. So, if they are equal, solid and liquid are equal, the free energy of solid liquid will be equal to free energy of solid along that line between solid and liquid. So, therefore, if I take a differential on both sides, this will also be equal, delta GL, dGL will be equal to dGS, and I know that dG is given by VdP minus SdT. So, let us write down these two on the both sides, then we will put the symbols VdP SdT. So, this is L, this is L, this is S, this is S. So, now if I just do the mathematics properly, what do I get? I get dP by dt is equal to dt. So, therefore, it will be SL minus SS divided by BL minus BS. That is what I will get. This is nothing but change of entropy divided by change of volume when the transformation from solid to liquid happens or liquid to solid happens. So as you know, in a what's called in a system like water, this volume change is negative because solid has a higher volume than the liquid, ice has lower density than the liquid water. So that is why this is negative, that is why the slope is negative, because delta S cannot be negative. Now delta S can also be written like this way, delta S is nothing but entropy of fusion, that will be equal to latent heat divided by melting temperature. So that means this is equal to L latent heat divided by Tm into delta V. So as you can see, latent heat cannot be negative, Tm cannot be negative because these are absolute values. So therefore delta V is negative in ice water system, and that is why this is negative sign, correct. So this is known as Clapeyron equation in the literature. This is what is derived in the slides. This is known as Clapeyron equation, this one. So I write down again, I remove this part. So dP by dt L by Tm delta V is known as Clapeyron equation. What is Clapeyron equation? Is this. This is Clapeyron equation. Some people say this is Clausius-Clapeyron equation, but I have two scientists, they have derived. So Clapeyron equation tells you how the pressure will change as a function of temperature for a pure component, correct. So let us now move ahead. Okay, before I move ahead, let me just also try to solve a problem, because you will be solving many problems in your assignments or something, because some of the cases it is important to know how to apply this rule. Let us say there is a problem which I will read out to you, that pure nickel I hope I understand, melts at 1726 Kelvin at 1 atmospheric pressure. Determine the melting point of pure nickel when it is acted upon by a pressure of 10 to the power 8 Pascal. Okay. So pure nickel melts at, suppose when pressure is 1 atmosphere, pure nickel melting temperature is equal to 1726 Kelvin. Now if I apply a pressure of 10 to the power 8 Pascal, what will be its melting temperature? You need certain values, and these values are actually latent heat and delta V. So what is the latent heat values given in this problem? Latent heat is about 18,079.2, 18,079.2 no 18,000 something wrong, 18,000, yes, 18,079.2, I am only writing wrong, 79.2 joule per mole, and this is 0.026 10 to the power minus how much 3 minus 6 sorry meter cube per mole. So this is my problem. I need to find out the melting temperature of pure nickel when this much pressure applied. So very simple, I just write down dP by dt, I borrow this Clausius-Clapeyron equation. This can be written like this, is equal to latent heat by Tm delta V. Now put all the values. So delta P is the pressure difference, 1 atmospheric pressure is equal to 10 to the power 5 Pascal, please remember this. So therefore this is 10 to the power 8 minus 10 to the power 5 divided by delta T, this is the pressure difference, latent heat is given 18,079.2 joule divided joule per mole, melting temperature is 1726, this is given 0.26 into 10 to the power minus 6, you can put down all the units, it will be equal. So the value which you will get is equal to I think 2.48 Kelvin delta T. So delta T will be 2.48 Kelvin if you do the maths properly. That is how it can be solved. This is a very easy problem, one can do very easy to test his knowledge on that. Okay, now let us move on and see the other parts of the diagram. So if I now, so this is what I have done, this diagram tells you exactly what I have done for the solid and liquid. Now I do for the liquid and vapor, okay, and solid and vapor both. So I draw a green curve, you can see on the G versus temperature curve, I draw a green curve corresponding to vapor. So this is corresponding to solid, this corresponds to liquid, the green curve corresponding to vapor, water vapor. So you can see the green curve cuts both the solid curve and the liquid curve. Let us follow one by one, okay. If I have one atmospheric pressure, I know the water boils at 100 degree Celsius temperature, we all know 100 degree means 373 Kelvin, 273 plus 100 is 373 Kelvin, everybody knows. So therefore this line which corresponding to the solid vapor equilibrium will be cutting this atmospheric pressure, one atmospheric pressure at 373 Kelvin. So now I can have 3 equilibria, solid liquid, solid vapor, liquid vapor. These 2 equilibria, solid vapor, liquid vapor is exactly same way measure as the solid liquid equilibrium measure I have shown you, okay. Now I will do the maths later, but let me just do all this stuff. We can apply Clausius-Clapeyron equation and get that, let us forget about those things right now, okay. Now let us go ahead and see the phase diagram properly, okay. So now actually I can see there are 3 lines, one solid vapor, solid liquid, vapor, liquid vapor, 3 lines on this diagram, pressure versus temperature. This is basically phase diagram of water, exactly, okay. And you can see the melting temperature is 273, the 373 is the boiling temperature, and this point where the 3 curves, solid liquid, liquid vapor and solid vapor, 3 curves meets, it is known as the critical point, okay. And these are the regions of solid, this is the region of liquid, this is the region of vapor, okay. So this is solid, this is liquid, this is vapor. So what is this transformation between solid and vapor? This is known as sublimation, very simple to see. Suppose if you take out, in a very moist day in a winter like December, if you have a rainfall and you open the refrigerator, you will find vapor of water vapor is coming out from ice. That is because sublimation happens very easily at the temperature and pressure. Similarly liquid, if you boil water it will form vapor. So this line corresponds to liquid vapor equilibrium, this one is called solid vapor equilibrium, and this one is basically solid liquid equilibrium temperatures. This is what I have written. So let me just remove my writing so that you can see it properly. So you have got the idea that this is actually way the phase diagram of a single component system is measured or determined. Now I just wanted to use this Clausius-Clapeyron equation even in this lecture, Clausius-Clapeyron equation again, and solve a problem for you so that you can do it, okay. I just skip it this part and remove everything in and do the things for solid vapor, okay, or liquid vapor rather. Let us do for liquid vapor, it will remain same. So for a liquid vapor system, liquid vapor phase equilibria, along this liquid vapor phase equilibria line, liquid vapor phase equilibria line, the free energies of solid and liquid vapor will be same, that is very easy to understand. So therefore the differential also will be same. So therefore V dP minus S dt, that is why I have derived this expression in the class before, V dP minus S dt, this is liquid, this is liquid, this is vapor, this is vapor. So what is dP by dt? Very simple, you have already done that. This is nothing but, okay, let me write down SL minus SV, oops, is it correct? Yes, SL minus SV, and this is VB minus VL, no, this will be SV minus SL, okay, that is correct. So now I know that for any liquid vapor system, volume of vapor will be much greater than volume of liquid, that is obvious. Volume of the vapor will be the volume of the container minus the volume of the liquid when which you are boiling the water, right. You could take a big container, put a small amount of liquid, when it boils, except the liquid wherever present, whole volume will be occupied by vapor. So that means volume of vapor will always have the volume of liquid. So I can write down V minus VL is almost equal to VV. So that means this is equal to SV minus SL by Vv. And if I apply the gas law, that what is the gas law? Pv equal to RT for 1 mole, then I can write down this one delta S divided by delta S V actually divided by RT, okay, RT into P, correct, that is obvious. So what is delta S? Delta S is nothing but, this can be written like this is a latent heat of vaporization divided by RT square, because LT by T here into P, right. This can be written like this, this can be written like easily like this. So I get this expression dP by dt equal to this. So now I take out this expression here and solve this. So I can write down dP by P is equal to LV by R dt by T square, right. So if you integrate that, you will get log of P equal to minus LV by RT plus a constant, that is integration constant if you integrate on both sides, okay. So this means log of P is equal to LV divided by RT plus, suppose integration constant is log of A, we can always have change that. So P is equal to A multiplied by exponential minus LV by RT. So you can clearly see the curve between solid and vapor and liquid vapor will be exponential in nature, and that is easily obtained from this diagram. That is easily obtained from this diagram. Very carefully it can be proved by the free energy equilibrium free energy equations that the equation of these two curves of equilibrium between solid and vapor and liquid vapor, let me just take it down again to show you this line, this curve, this is basically a curve and this is also a curve. These are equilibrium between solid vapor and liquid vapor. They will be exponentially increasing line, okay. That is what is basically shown in this diagram very nicely. Now one can actually solve a problem to know a better idea of this equation. So let me just do that, then I can get back to you in a detailed manner. How I can do that? I just skip this part and remove this particular portion for your benefit, but I urge you to do these problems or do this derivations yourself, otherwise you will not be able to understand or solve the problems in the exam. Let us suppose vapor pressure, the problem is like this, vapor pressure of pure magnesium in the temperature range, so pure magnesium vapor pressure in the temperature range of 700 to 739, 700 to 739, I think we should, to 739 Kelvin is satisfied by this expression. What is that? Log of P is equal to minus 1700 320 divided by temperature plus 19.78. This is for pure magnesium. So again for pure zinc, same kind of expression valid for the temperature range of 575 to 630. Why this temperature is given? Because they at this temperature only evaporation happens. So this is given by log of pressure pure zinc. Okay, I forgot to write zinc. Log of P is equal to minus of 15,636 divided by temperature plus 20.66. Okay, the question is that determine the heats of sublimation. That means determines the heat of sublimation for magnesium and heat of sublimation for zinc. How will you do that? It is very simple, anybody can do that, there is no problem. I have to compare this expression with this, okay. How do I compare? This one log of pressure is equal to minus LV by RT plus log of A. Okay. So that means this one is equal to this term 17,320 by temperature is equal to LV by R, correct. So for magnesium I can write down LV by R. So let us do for magnesium first. Okay. LV by R equal to minus LV by R equal to this will be minus will get cancelled 1700 320. Okay. So LV is basically this multiple by R, and R has a value of 8.314 basically joule per mole per Kelvin. So that's it will give you 100 and something like 144 kilojoule per mole. This is sublimation of lit attentive sublimation for the magnesium. Similarly, I can compare zinc one with this equation, log of P equal to minus LV by RT plus log of A. With this, you can see here that for zinc, LV zinc by R is equal to LV zinc by R is equal to minus of this one minus plus of this one, because minus will get constant. So therefore LV zinc is equal to something like 130 kilojoule per mole. You have to know the value of R. Value of R is 8.314 joule per mole Kelvin. Okay. So that's actually a way you can actually solve these problems. We can solve many problems, and I will give you some problems also to solve in the interest of yours, which you can do yourself. These are very simple, even class 12 standard problems which anybody can do. That is not a big issue. So you understood the basic phase diagram. This is called urinary phase diagram in PT space. Therefore, urinary phase diagrams will be in pressure temperature fields or space. And okay, now let us go in detail of this diagram. This is another such diagram again for water system, water like system. This is the line for 1 atmospheric pressure, and this is the normal boiling point because it make a cross section with the liquid vapor. This is the normal melting point because it cross section with the solid liquid. Normal boiling point, the temperature at which the saturated vapor pressure excited by the liquid is 1 atmospheric pressure. That is why I have drawn a 1 atmospheric pressure horizontal line. Now this point I told you this is known as tipple point. Why? Because at this point both liquid solid vapor coexist. Okay. And very rarely you find this happens for water system, because this is a point at which only this can happen. Now I just drawn several lines for that. Okay. Saturated vapor pressure of solid, saturated vapor liquid. So what I will do for the next 8 minutes or so in this lecture is that I will show you how to apply phase rule. So let us apply here. As you know, phase rule is basically given by what? Forgotten, right? Phase rule is given by this equation. What is that? F equal to the degrees of freedom F is equal to C minus P plus 2. Why 2? Because when pressure and temperature both are changing, that is why. So F is the degrees of freedom, C is the number of component, P is the number of phases, and 2 is this. So now in this system, this is a single component system, C is equal to 1 because component is 1. So F is equal to 1 minus P plus 2, that is equal to 3 minus P. So P is the number of phases. So now for a field like liquid, only one phase is present, P is 1. What will the value of this P is 1, F is 2. What is the meaning of that? So I mean to say is that in the area liquid, whole liquid or low vapor or solid is present in this area marked as a blue, green and pink. Within that F value is 3 minus 1, that is 2. Clearly the gives phase rule tells. What is the meaning of this? Okay, let us very simple. So if I draw a line here like this, okay, let me change the color of chalk, it is not visible. Okay, I draw a line here and erase the other line. Okay, so this line is basically at a constant temperature P1 suppose. Now the meaning of F equal to 2 is that in this case F is equal to 2 is that, what is the degrees of freedom equal to 2 is that I can change both the pressure and temperature simultaneously. Suppose I have this pressure, now I can choose as many as temperature possible, you can see here, but still I will remain on the vapor phase, liquid phase. Similarly, if I change the pressure, I can again see that at many temperature this liquid will be present. So this is the meaning of F equal to 2. Same thing will be valid for vapor field and liquid field. Now this is not the case when you do it for on the line. On these lines, this line or this line or this line, the two phases are present, liquid and solid, solid and vapor or vapor and liquid. If two phases are present, so here suppose on this line two phases are present, P is equal to 2, so F will be equal to 1, because 3 minus 2 is equal to 1, 3 minus 2 is equal to 1, okay. So what is the meaning of that? That means very simple. If I choose the pressure, suppose here like this, if I have the permission to choose the pressure, I can choose this pressure, my temperature is fixed at which both solid and liquid and vapor can coexist. I have no choice of temperature, I can't choose. That means I have 1 degree of freedom, I can only choose the pressure or the temperature. Similarly, if I choose the temperature, then I have no choice of pressure, pressure is fixed because it is on the line. That is the meaning of degrees of freedom equal to 1. Degrees of freedom equal to 1 means I have only one freedom, that is either pressure or temperature to choose. If I choose one of these two, then other variable is automatically fixed by the equilibrium condition. That is what is the meaning of this. So that is what is the meaning of the F equal to 1. So now there is a point, special point in this diagram in which all the three phases coexist. That means at this point, triple point, number of phases equal to 3, P equal to 3. If P equal to 3, F becomes 0. So that means at this point F is equal to 0. So that means I can't change pressure, temperature, anything at this point. These are all fixed because this is a point. The moment I change pressure a little bit, all the three phases will not even coexist. They will change, equilibrium condition will be changed. Or if I change little bit of temperatures, equilibrium condition will change. The meaning of this F equal to 0 is that I do not have any freedom to choose any of these processing variables, pressure or temperatures in my disposal. So this point F equal to 0 is known as invariant point. Invariant means I can't vary, this is F equal to 0, okay. And F equal to 1 means univariant point. Univariant means I can vary one of the variables, pressure or temperature, not both. F equal to 2 means bivariant. So I can vary both simultaneously, pressure and temperature. I won't change the phases. So that means within this colored areas between solid and liquid, solid or liquid or vapor, I have a bivariant system. On these lines I have a univariant system, and on this triple point I have invariant system to exist in a water liquid phase diagram. So let me just quickly show you the actual phase diagram. Actual phase diagram looks like this. This is ice, this is water vapor. You can clearly see this curve is a negative slope because of the thing I explained, and these are all both look like a exponential curve actually. The values are given. For triple point, pressure is 0.006 atmospheric, temperature is 0.01 degrees Celsius. Similarly, for carbon dioxide, you have a solid, liquid, vapor. There is a triple point here, there is a critical point there for the liquid vapor also. We will not discuss a critical point right now because that comes a different separate things. Pressure and temperatures are shown here. Everything happens sub-zero temperatures for carbon dioxide. There is something known as dry ice, okay, for carbon dioxide. Solid carbon dioxide is known as dry ice, which can be prepared at a very high pressure. That is what you can see here at lower temperatures. You have to go to below about say 20 degrees Celsius and apply pressure about 1000 atmospheric pressure to get dry ice. This is for sulfur, okay. Sulfur has rhombic sulfur, monoclinic sulfur, and they are actually having a triple point with the gas, and there is a liquid at high temperatures. So, liquid before sulfur become liquid it transforms to monoclinic sulfur, we all know that. So, this is what the sulfur phase diagrams are done. You can search on Google, you will find out all this phase diagram very nicely, even the values are given. So, by this I just wanted to show you at the end the phase diagram of iron, which I have already shown to you. See, iron has alpha phase, gamma phase and delta phase. Alpha and delta are BCC, gamma is FCC. And you have also, this is actually beta, which is known as ACP phase at a higher pressure, about 18 gigapascal. This pressure is this ACP iron is present, and at a very high temperature it becomes liquid. And these are the slopes of these different curves. You can see this is negative, this is positive, depends on the change, delta V change. Delta V is basically dictates the slope of these curves. Okay, slopes are given here. This is negative, this is positive, and this is also positive. So that's how actually we can actually explain the different unary phase diagrams. So next time I come, I take the next lecture, I will be spending little bit time on these diagrams again, and then move ahead for the binary phase diagrams.